Here we go. Okay, let me share my screen. Before I start, just wanna say it again, your video project due on the Monday, not next week, the week after next week, okay? In case some of you didn't hear it last time, okay? I think this week I will post the grading criteria, okay, on the Moodle, so you will see, and then you can prepare based on the way I grade, okay? So the goal is for you to actually do some experiment and measure some temperature and to verify the conduction equation we use, right? Okay, so, okay. Chapter 2 is conduction, right? In depth on the conduction. Monday, we introduced this thermal, hold on, somebody is waiting. Okay, Monday we introduced this thermal resistant, the idea of the R, the coefficient R, right? Thermal resistant. For the simplicity of for the convenience in the calculations. So both conduction, convection, we can actually share the same equations if we use the thermal resistance idea. Okay, so this seems like a better equation for everybody to remember, right? Heat transfer rate just equals to delta T divided by that resistance. We borrow this idea from the electrical circuits, okay, in which the current I equals the voltage divided by the resistance, right? So it's a similar idea here. The delta T is similar to the voltage. Q sounds like the current, electrical current. And the thermal resistance is just equivalent, similar to the idea of the electrical resistance, okay? So in that sense, we can explicitly separately determine the thermal resistance before the calculation based on the serial arrangement or based on the parallel arrangement, okay? The serial arrangement is much easier, just the summation of the resistance. This here shows the parallel arrangement, okay? In the parallel arrangement, similar to electrical circuits, right? This is how we calculate the 1 over RA plus 1 over RB plus 1 over RC, right? That's the thermal resistance, overall thermal resistance. Okay. So this is for the conduction. What about convection? I said, hey, this equation we can use for both conduction and the convection now. We don't have two equations to remember. Now you can, if you remember this one, that's about it, right? You can just use it for convection also. So what about in convection? What is the thermal resistance? Okay, so let me turn another page. Let me rewrite this equation here. Okay, so let's say we have a material, we have a conduction here, then we have a convection. So for the same idea, right? This is a convection, let's say. Inside is the conduction, okay? So we know the thermal resistance for the conduction. Conduction equals to, we showed it in the previous page, right? Is that right? Is delta X divided by K times area. Okay. How about convection? So you can write down the convection equation. Is that right? So does the convection thermal resistance equals one over H A? Okay. Is that simple? Okay. So that seems like on the page, textbook page 33, figure 2.5. Okay. 2.5, you have a situation like this. Okay, you have a convection Q1 in here. Let's say TA, external temperature, right? Then you have a temperature T1 here. You have a temperature T2 here. Then you have a temperature TB on this side. Okay. Let's say fluid A, fluid B, and this is the solid material inside. Okay. As the book shows, the temperature drops, you draw the curve like this, then drop from T1 to T2, then keep dropping from T2 to TB. Okay, seems like here the highest the temperature in the fluid A. Okay, in the other side of the solid is cold fluid B. Okay, so for this problem, you can simply easily draw a circuits. Okay, so in this end is TA, in this end is TB. Okay, two ending temperatures, A and B. So you have how many resistance there? 3, right? I already drew 3. How about the first one? 1 over H1, let's say HAA, fluid A. Okay, so the second part is solid, right? Conduction. Delta X divided by K over A. This problem is easy. It's a Cartesian coordinate. It's not cylindrical. So the cross-section area is the same. So it will be simple in calculation. So for the third part is the fluid B, right? It will be HBA. These are the 3 thermal resistance. You know, if you really want to mark the temperature, like in the book, you will say, hey, this is where the T1 is. This is where T2 is. Okay. So the overall heat transfer rate equals TA minus TB. Okay. If you want to use this equation, the delta T has to be the front temperature, the beginning minus the end. Notice this thermal resistance for the conduction, there's no negative sign in front of it. Remember that conduction equation is supposed to have a negative sign, right? Which means then the T, the order of the delta T, it's not the ending temperature minus the beginning temperature. So it should be beginning temperature minus ending temperature. We try to get rid of that minus sign, okay, in the thermal resistance for the conduction, okay. For the convection, the equation, it is beginning temperature minus ending temperature, right? It's the surface minus to infinite, right? So there's no sign change here, Okay, for that convention, if you use this equation, just remember the delta T has to be the beginning temperature minus the ending temperature. Okay, be careful, very careful. The signs. What did you say? So it's divided by summation of the thermal resistance. In this case, it's a serial arrangement, right? So it's just one atom together, HAA plus delta X over KA plus 1 over HBA. Okay. That's the heat transfer in this system, heat transfer rate. Notice the whole entire system, there's no heat generation, okay? There's no heat sink, no heat source. It doesn't lose heat. So the Q is the same. If you just want to look at between T1 and T2 in the conduction part, it has the same Q. Okay, it has the same Q. So I can really very quickly extend this problem to calculate the T1 and T2. Are you be able to calculate T1 and T2? If I give you TA and a TB, let's say TA is 100 degrees Celsius. I'm making up numbers in the book. It doesn't have this example, right? TB, let's say 20 degrees Celsius. Okay. Then I give you all the dimensions, delta X, the thickness of the material. I give you the cross-sectional area, okay? I give you the both H's. You know, basically, you know all the properties, okay? All the dimensions for this problem. Then you have the temperature, T and the TB. Will you be able to calculate T1 and the T2? Will you be able to?
You should be able to, because you said that the Q is the same all the way through. So once you figure out your Q, you can do individual conduction and convection to find T1 and T2.
That's exactly what's supposed to be. So this is the practical problem. If you know the two ending temperatures, if you know the property of the fluid as well as the solid, if you know the dimension for the realistic, you may even design a problem like this for experiment, okay? Maybe that's the second experiment, including convection. The first one, I just said conduction, right? So then you can actually predict the surface temperature T1 and T2 by doing the calculation. Okay, you can predict. Then you can even measure it, see what the difference between your measured surface temperature and the predicted surface temperature, right? This is kind of like a good example for experiment. Okay. Okay, everybody follow me? I think it's very important. I think the key idea here for the energy transfer, heat transfer, the key idea is in this kind of system, you know, the Q is exactly the same going through the system. Okay, let's make it a quiz problem. How about that? I'll give you numbers. Let's do a calculation. Let's find out the T1 and T2. Okay, get a paper and write it down, and I'll give you 5 minutes, maybe 10 minutes. Let me give you the numbers, okay, in the group meet group.
So, Dr. Zhang, quick question.
Yeah.
So, you said that the Q for each, you know, each convection and each conduction is the same.
That's
correct?
right. Yeah, that's correct.
So it doesn't diminish as it's going through.
It doesn't diminish unless you have a heat sink. But in reality, it diminishes a little bit because always there's a reduction. You know, you take the the heat, material has heat capacity or something like that. It will take away a little bit of your energy. But we are looking at the ideal case. So there's no heat loss. Okay, there's no, if I say, hey, there has to be a heat sink in there, then that means that, okay, there's some energy will be take away from the system. Okay, now we don't take away any energy from the system, then we assume it's ideal situation. Okay, so that Q rate is the same. Let's say, hey, I'll give you the cross-section area. Surface area is 1 meter square. Okay, let me write it down. A equals 1 meter square. Okay. Convection transfer coefficient, HA, let's say, equals 100 watt per meter square. Okay. It's hard for me to type the units. I just give you the number here. HB, let's say, is 50. Okay. What is the K? What's the material? I just make up a number, right? Whatever number you calculate, it's fine. That's K is 150. Okay, watt per meter square K, right? Okay. Delta X, thickness, 10 centimeter. How about that? Okay. To find the T1 and T2. I'll give it 10 minutes. How about that? It doesn't really need 10 minutes, but let's just do a practice. Every practice I give you, let's give you some awards, right? Rewards for doing anything. Okay. Write on the paper, take a picture, and submit through Moodle. Let me open the Moodle submission site. Okay. Go ahead. You don't have to talk to each other, right? This is really simple. Just practice it for your own good to remember this principle. Okay, go ahead, start. Take your time. I put the due time 11:30. Okay, give you a couple more minutes. Okay, it's there. Okay, let me give you 3 actual minutes. 11:33 due, so it will have 5 more minutes. You have actually 6 more minutes. Okay, 11:20. Oh, 28 now. Okay, 5 minutes. Okay, I think you have 2 minutes, 50 seconds about. I see 2 submissions. Let's see how long we have. Okay, you have about 1 minute and the 4 submissions now. Good, 6 submissions. You have 45 seconds. Okay, let's do this. I give you a couple more minutes, but I don't want to change the mood. If you cannot make the deadline 33, you email, text it to me. Not text, group me, right? got an 8. But that's a final extension for 2 more minutes. Okay, no more extension.
I submitted in the group me. Is that fine?
Yeah, as long as it's before 11:35.
In the group meet, that's fine, right?
Yeah. Okay. I got a Kalen, I got a Suresh, I got a Haley. Oh my good me. Okay, I think I got 10 summation through the Moodle. Okay, I got a Kelly. I got Reagan. Almost time, guys. I got a JC. It's okay, Kaylin, I got yours. I got a Kaylin. Okay, I guess that's it. Dawson Butler, also I got it. Time is 11:35, you're still fine. If the time shows 11:36, then I won't accept it. Okay, okay, that's it. So, okay, I think a couple of you asked me a question about the what is the Q, and so that's why I need to pay attention to my lecture now. Okay, I said it there. The Q is for the overall, right, from TA to TB, right? And okay, yeah. Let's we have 15 minutes. Let's do one more examples. Okay, that's example 10 point. Oh no, 2 point. Let me find the example. 2.4 on the textbook. Okay. Oh no, it's not 2.4. Not 2.4 yet. Okay, it's actually 2.1. Okay, 2.1. That's what we're going to talk about. Hold on. Okay, so let's see what the problem says. Okay, an exterior wall of a house may be approximated by a 4-inch layer of common brick. You get a K. Okay, the first layer brick, K equals 0.7 watt meter K, right? C and K, doesn't matter. And the thickness 4 inch. Okay, then gypsy, then is the gypsum plaster, 1.5 inch. Okay, outside, right? And then you also have a K 0.48 watt meter C. Okay. what thickness of loosely packed rock wool insulation? Then another insulation possible, which give you the K equals 0.065 watt. Let me see. So what is the thickness of this insulation? Should be added to reduce the heat loss by 80%. Oh, reduce the heat loss by 80%. We want to decrease Q.
Dr. Zhang,
Yes.
what problem did you say this was?
Example 2.1 on page 31. Decrease Q by 80%. Okay, that's a goal. Okay. That makes sense. So this is the interior of the room. Then you have brick, you have gypsy plaster, and the possible of insulation. Okay. First layer, second layer, and the third layer. So you have interior temperature, right? Inside. T is outside. Okay. So basically you have a constant Q goes through. Okay, so that's the Q. So you in this kind of case, the strategy is always compare two situations with or without insulation. Let's say this case is with the insulation. Another case is without insulation. But see, outside temperature is the same. Inside temperature is the same. Inside temperature is controlled by your AC, right? So, okay. So basically you compare these two situations. So you have basically 3 resistance. And here you have 2 resistance. And that's it, right? So R theta 1. No, not R theta 1, R thermal resistance, RTH 2. RTH 3. So this is RTH 1, RTH 2. So Q, this is a QA situation, this is a QB, right? B situation. So QA will be, what does the problem say? 80% decrease in the heat loss. So 80% decrease of the heat loss. So QA over QB equals what? %80 decrease, so it's 20%. Is that right? The heat transfer. So you have insulation, basically is to reduce the heat transfer rate. Is that right? So you have actual insulation here. So your heat transfer rate reduced to 20%. Okay, is that right? So how about the relationship between the thermal resistance? Is that also 20%? With insulation, let's say situation 8. Does that also equals? Do they also equal? Well, again, Q equals to delta T divided by summation of RTH, right? Is that right? So in this problem, think about the practical situation. Inside the room, temperature is T1, outside air temperature T0, okay? So the delta T doesn't change. It's a constant between these two situations. Do you agree? Okay, if QA is 20% of QB, how about R theta? It's in the denominator. See, I wrote it wrong. That's why I put a question mark here. That should be equals, if you're gonna remove the question mark, it will be B over A. Is that right? Without insulation and with insulation. Okay. So if you don't see this, I can write both equations down here. The same delta T over summation of R theta B. Okay. So if delta T, they are the same, QA over QB is 20%, then RTHB over RTHA should be 20%, right? So they are equal. Okay, it's very important to flex the equations back to the reality, right? In the real situation. So the difficulty of this problem is you have to determine that the delta T in both situations are the same. Okay, is that right? Everybody agree? Okay. The reason I bring up this example is I think a lot of you, many students, for the problem like you have to compare two different situations. This type of problem, some of you will have difficulty on solving this. But to me, you can just write down the equation for the two situations, then look at what are the same and what are the difference, and then you can find the relationship. So in this case, in this problem, this is the hidden situation, hidden information, not directly stated by the problem statement. Okay, the problem just tell you, hey, with insulation, the heat transfer is decreased by 80%. It didn't tell you anything about the overall thermal resistance. What's the ratio between these two cases? But you have to determine that. Okay, that's the key of this problem. So how thick the insulation is. Then you can just expand this summation R THB and the summation R THA, the two cases, right? Okay, put the ratio and you can calculate it. I can show you on the next page. B is without insulation, A is with, right? So without, so it's theta 1 plus RTH2. Both of them are given. Okay, it's just conduction, right? Is that right? The two material. They give you K and they give you K as well as the thickness. Okay, so delta X divided by K. Area doesn't matter, right? Area actually, it's the same area everywhere, so it can be canceled, okay? Top and bottom. So basically it's just delta X1 divided by K1, both given, right? K2. Okay, so you should be able to calculate it. It's equals 0.22. 0.224 meter square Celsius per W. This is the unit of the thermal resistance, okay? So how about in the situation A with the insulation? It will be the same RTH1 plus RTH2 plus RTH3. So RTH1 plus TH2 is 0.224. How about RTH3? That's the thickness, which is your unknown, right? K is given. Okay, K is given. So in that sense, K is given. This is your only unknown because you have this relationship. You can plug in this equations, okay? 0.224 divided by 0.224 plus delta X3 over K. What is the K value? 0.065, right? So equals 0.2. So delta X3, the thickness of the insulation, will be 0.0584 meter. It's approximately 2.3 inch. Okay, it's about 6 centimeter. Okay, 6 centimeters, so about 2 inch, a little bit more than 2 inch, 2.3 inch. Okay, so this is the example. Okay, I think this is a good problem. Okay, it's a hidden information from the problem statement. Always, it's up to you. It's your responsibility to dig in the hidden information. This problem, it tell you the heat transfer rate, the ratio is 20%, one to the other. Okay, but equivalent to tell you that the thermal resistance, overall thermal resistance between without insulation and with insulation, that ratio is actually equal to 20% too. Okay, okay, based on that, that's the second page here. Okay, so you should be able to calculate the required thickness of the insulation for this problem. Okay, I guess that's it for today's class. Any question? I have 1 minute.
Yeah, someone else had asked, but what problem is this? I'm looking at the book and I'm just not seeing it.
Huh? This is 2.1, example 2.1 on page 31 in my textbook. Is that your question? You couldn't find it on the textbook?
Oh, okay, I see it. It starts all the way at the bottom of the page.
Yeah,
Okay.
start all the way bottom. Yeah, yeah. Okay. Okay, so good. Have a good day. So, and see you on Friday. Okay.
Dr. Ning,
Yeah, yeah.
I had some internet trouble sending my PDF. I sent it to you in GroupMe and on Moodle. Will I be counted off?
Yeah, you send it late. Let me be fair to everybody. So if you turn in later than 11:35, I'd still take it, but I give you a little bit reduction. How about that?
It says on GroupMe 11:36.
Yeah, on mine is what's your name, Andrew?
Yes.
Yeah, yeah. You passed 11:35. On mine actually it shows 11:38. So I will take a little. Don't worry about too much. Just a little to show the. To be fair to everybody, if you submit on time, you know you get the. If you're a little bit late, you take a little bit off. How about that?
I guess.
Yeah, just try to.
Dr.
Make sure.
Zhang.
Yeah.
I had a question for the quiz when I was working through it. So I know in the big overall Q we had the delta X and all that because of the thickness. When we're solving those individual parts with T1 and T2, is it okay to just say that it's negligible because it was right there, like outside, like it didn't go through the whole course, or would you have to actually include it?
You don't have to say it because I already said it. The overall Q is equal to the individual Q for each
So
part.
you just set like the Q equal to just like
Yeah, there's no that's total heat transfer rate the same inside the entire system.
So yeah, like you would just use either the convection or conduction formula, not it put together, to solve for T1 and T2.
When you calculate T1, T2, you probably need to find the T1 first based on the convection part in the fluid A. Okay, then you can use the conduction between T1 and T2 to find out T2, or you can T2 you can calculate it based on the convection in the fluid B. So,
Okay, yes. I just you said something I caught on. I didn't even think to use the conduction formula. I could go if I solve for T1.
Now do you understand? See,
yes, sir.
that's my process. And it's not. Don't worry about the grade here in the quiz. You get 100 of a quiz in the semester. Doesn't matter. But go through this. Maybe make you understand. Make you know how to do this.
Yes, sir. Thank you.
That's a goal. Okay.